Let me thank the organizers for the opportunity to be here and make the talk. I would like to speak about the connection between so different things like models of random matrices, Laplacian growth or Hele-Shaw flows, and Hurwitz numbers. This work was done with collaboration with many people. Among them are Paul Wigman, Mark Minet-Weinstein, Igor Krichever, Eldad Bettelheim, Adet Agam, and most recent developments were done together with Sergei Natanzon. For the introduction, I have listed here 4 very different topics from physics and mathematics. To the left are some general areas like viscous hydrodynamics, and to the right is a list of more concrete parts of these areas which I will be speaking about. Paul told us about anomalous hydrodynamics, and this I have in mind just standard hydrodynamics, but very viscous, when the liquid moves because of the driving force with just a difference of pressure. So no vorticity, just gradient flow. And this, I will speak about this in more details later. This is also known as Hele-Shaw problem, or more general as Laplacian growth. This means that this kind of motion exists not only in hydrodynamics but in many other contexts. And the common feature is that the local velocity of an interface is proportional to a gradient of some harmonic field. Because of this, it's called Laplacian. It appears that all these topics are related somehow because all of them have a common integrable structure, which is two-dimensional Toda lattice hierarchy in the dispersional limit. Actually, few of these, namely the last two, have this structure, even the structure of full Toda lattice without any dispersionless limit, and it's intriguing whether it can be generalized to the first two. What does it mean in this context? The second one is a purely mathematical problem, the very classical. This is complex analysis in 2 dimensions. And such problems like inverse potential problem or Dirichlet boundary value problem, which is related to the Riemann mapping problem, that any simply connected domain can be conformally mapped to any other simply connected domain. So in this, this is a theorem, existence theorem. It doesn't give you a prescription how to find this map. And this integrable structure probably can say something about this. It can give, though quite complicated, but still something, some receipt how to find this map. And a very unexpected connection is the third one. With this is about geometry of ramified coverings for Riemann surfaces. Actually, this was known in the literature for some time. This relation was discovered by Andrei Okunkov, and it is also for full Toda hierarchy. And in the dispersionless limit, we get coverings of genus 0 surfaces. I will speak about this later. And it's very amusing that these two are related. For example, the second one and the third one. It would be very interesting to find a direct relation between them. But at the moment, I don't know how to do this. And at last, the random matrices. All these topics have behind them somehow the model of normal random matrices in the large n limit. Okay. Let me start with random matrices. So with the normal matrices. So we have normal matrix, which means that it commutes with its Hermitian conjugate, and the standard integral over the space of such matrices with some natural measure, which is induced by embedding of this manifold of normal matrices into all complex matrices, with some constant, independent constant Cn here, and in general arbitrary potential W, which can be, for normal matrices, it can be any function, any reasonable function of two variables with the property, some reality property. So this, for the connection with integrable systems, it's better to write this function in the following way. So to separate harmonic part, you see here we have m and here m dag with some coefficients, which are going to be commuting flows of the infinite dimensional hierarchy of integrable equations. And the rest is non-harmonic part, this function u, which will play some important role in what follows. And the simplest example is just product m and m dag. So this is expression known in the context of model of two Hermitian matrices instead of normal. Of course, we can, as usual, we can rewrite this partition function in terms of eigenvalue integral. So it depends on the two sets of constants, which I call times, because in some applications they play the role of times. So we have n-fold integral over the whole complex plane. In general, here we have the van der Monde determinant, beta equals 2. Here we have external potential. So the connection with integrability comes at this point. So it is a function of these parameters. This partition function is a tau function of the two-dimensional Toda lattice hierarchy without any dispersionless limit, like as it is for any finite n. And n itself plays the role of zeroth time in the Toda lattice hierarchy, the discrete one. The dispersionless limit is equivalent in the Toda lattice hierarchy is equivalent to the large n limit in this matrix model. And this limit goes as follows. It's convenient to introduce the constant h bar here, like Planck's constant, kind of Planck's constant, and tend n to infinity and h to 0 in such a way that their product, which I call T naught or simply T, is fixed. T because in the application to viscous flows, this is just a physical time. This variable is going to be the physical time of the problem. In the limit h goes to 0 and infinity, this tau function or partition function behaves like this. It's exponent of some, it's non-analytic in h, so it has an essential singularity when h goes to 0. But we can separate the rest, and this function f is already a smooth function of its variables, can be expanded into this Taylor series. Of course, it has some singularities, but there is always a region where it is a good function, even a real analytic. So we'll consider only the first term of the expansion in h bar, so this series can be developed further to higher powers, and all this is very interesting, of course, and has some meaning, geometrical and so on. But today I will be restricted by the very first term. In fact, this leading approximation is very simple because it does not require taking an integral. The integral in this approximation is equal just to the maximal value of the integrand, as usual in the steepest descent method, or like this. Like a very classical approximation. No fluctuations. So if we introduce the microscopic density of eigenvalues, normalize it, put in h bar here, then we can see that the eigenvalues fill some domain in the complex plane. It may be multiply connected, it depends on the potential, but let us consider the simplest case when it is simply connected. And this domain is characterized by the property that the density inside it is not zero when n goes to infinity, and outside it's zero. So this is support of eigenvalues. And the density inside it is proportional to the Laplacian of the potential. So it's kind of a background, the compensation of the background charge. So there is background charge with this density, which creates the potential, and these eigenvalues, which are point-like charges, just compensate it. So full screen. Okay, but the shape of this domain, shape of the support, how to find it is a much more complicated problem. All what was before was elementary, and this one is a very serious problem already. It's equivalent to the inverse potential problem, which is very transcendental, cannot be solved effectively. Example, the simplest example, when the potential is of this form, so the density is constant in this case, and it appears that these coefficients tk should be equal to the this equilibrium when the charges are in equilibrium state. Then these coefficients should be equal to the harmonic moments of the exterior of the support of eigenvalues. And the area of this domain should be equal to t, or t naught. These parameters characterize the domain, at least locally, and the shape. To find the shape, you should solve this inverse problem: how to find potential from coefficients of the multipole expansion. Okay, now let me restart with similar data. Without any reference to random matrices, and reformulate this solution in the leading approximation in somewhat more mathematical terms. So what are our data? We have a function u, this matrix model potential. It may have some singularities, but let us assume that it's not too singular. And the Laplacian of this function is the background charge density, and we assume that it's always positive. So the interpretation of this function sigma may be different. It depends on a particular problem. It's background charge density, or in some applications it's conformal metric. There are two important examples. One of them I already mentioned. This is probably the simplest example when this density is constant. And another one is like this. It's the potential looks rather complicated, square root of logarithm. But the density is not very complicated. And there are two parameters, q and beta. They will play a role at the end in applications to Hurwitz numbers. These parameters, but here they just have a meaning of the beta is somewhat strength of this potential, and q plays the role of a cutoff in the z plane. Okay. Now we have a simply connected domain D. Let us assume that origin is inside it. The boundary curve is gamma, and the complementary domain is denoted as DC. So now let me introduce generalized moments of the exterior. Now we have function sigma here, so it was equal to 1 in the previous example, but in general we have these moments of the distribution of the charges, which can be rewritten as a counter integral due to Stokes' theorem, and also the T0 variable, which in this case is equal to the total charge concentrated inside of this domain. Similarly, we can introduce complementary moments, moments of the interior. So the such integral with positive powers of z over interior, which also can be rewritten as a counter integral, and logarithmic moment, the one complementary to T0, such logarithmic moment. Their meaning is very clear from simple electrostatics arguments. So let me consider the potential which is created by the background charge inside the domain, and no in zero charge outside. So integral over the interior domain D. Then we can expand it in the interior around zero or around infinity in the exterior. And the coefficients of the Taylor expansions are just in front of harmonic terms, are just this constant moments Tk and complementary moments Vk. So this should be very clear. Now, important theorem that these real parameters, or that consider only moments of the exterior. So it appears that they would uniquely characterize the domain, at least locally. In the sense that they are local coordinates in the space of simply connected domains. In particular, the complementary moments, Vk, are functions of Tk. So this means the meaning of this theorem is as follows. If we have any one parameter deformation of the original domain with parameter t, some real parameter t, and all harmonic moments, including T0, are constant, so if they are preserved under this deformation, then this deformation is trivial. And second property, that these parameters Tk are in fact independent. So for each shift of Tk around some given domain, we can find a domain corresponding to this shift. So this deformations of the domain, which change only one moment, can be constructed using the Green's function of the Dirichlet boundary value problem in the exterior of the domain. So this G is the Green's function. So I separated the logarithmic term, the singularity at coinciding points. The rest is regular. And the property is that, first of all, it's symmetric function equals 0 on the boundary when any of the arguments is on the boundary. And this function, the rest is harmonic everywhere outside the domain. So this Green's function solves the formally solves the Dirichlet boundary value problem to restore harmonic function from its boundary value. So the Poisson formula solves this problem. Now, if we know the conformal map from the outside of this domain to the exterior of the unit circle, then the Green's function can be constructed using this formula from textbooks. And we normalize this conformal map in the following way, that we say that infinity goes to infinity and the derivative at infinity is real positive. In fact, this formula does not depend on the normalization, but just for convenience, let me consider this normalization. Then this conformal map can be expanded into a series around infinity. Now, how we can describe deformations? It's convenient to describe them in terms of normal, small normal displacement of the boundary. So at point xi, we shift from the boundary with positive sign if we go outside and negative if we go inside. And this delta n is just the distance of this shift. And consider there's some special deformations constructed with the help of the Green's function. We fix a point A somewhere outside the domain and say that the normal displacement is proportional to the normal derivative of the Green's function with respect to the other point which is on the boundary. So the function itself equals 0 if z is on the boundary, but the normal derivative is not. It's something. So this is a well-defined class of deformations if epsilon tends to 0. And the deformations which change only one moment can be constructed using this Green's function. So consider such a function and consider the deformations of this form. Then it can be shown that this one changed only real part of the harmonic moment, and this one changed only imaginary part. And if we put this point A to infinity, then this deformation which corresponds to this point just equal to the normal derivative of this Green function, which is actually logarithm of modulus of the conformal map. This deformations change only t naught. Now let me introduce differential operators, which are very convenient in this business. So they are generating series of derivatives over all harmonic moments. And introduce such differential operator, which is sum of these three operators. And then the important lemma, easy but convenient, useful, a very useful lemma is that under this special deformations with the base point z, taking this deformation is equivalent to applying this differential operator to any functional of the domain. X is any functional of the domain, which I assume to be a function of the harmonic moments. As soon as they are coordinates, we can consider any reasonable functional as a function of these parameters. Then applying this differential operator to this function, we get at the point z, we have this special deformation with the help of this of the Green's function, this one. Okay. Now, what is in the limit? We have this free energy of the. This quantity is just the free energy in the matrix model context, and here we can just introduce such a function. This is a functional of the domain, and I would like to regard it as a function of this parameters tk. Then the claim is that this is the dispersionless limit of the tau function, in the sense that it is, you remember, the limit was the limit was e to the 1 over h squared times f, and this f is called sometimes it's called dispersionless tau function, although the tau function itself doesn't exist in this limit. Its logarithm, rescaled logarithm, exists. And the claim is that this function f is exactly a function of this class. So an easy theorem is that when we apply this differential operator to this function, we get this, and you see here is it is a potential created by the charge. So if we expand it around infinity, we get relations that the complementary moments are just derivatives, first-order derivatives of this function with respect to moments of the exterior. Next theorem is about second-order derivatives of this function. You see that this object is a kind of generating function of all second-order derivatives, because here you have any combinations of applying derivatives with different indices. This is the singular part, and the claim is that what you obtain is exactly the Green's function of the Dirichlet boundary value problem. Corollary is that the conformal map itself is given by this formula, which contains only holomorphic derivatives. This one, we have all of them, holomorphic and anti-holomorphic, and if you separate the holomorphic parts of this formula in both variables and tend one of the variables to infinity, you get this simple formula for the conformal map. In this sense, it provides a kind of more effective prescription how to find the conformal map, because this function sometimes can be found as in the form of a Taylor series. So it's much more constructive than it was before. Before it was nothing. This one is rather complicated, but still something. Okay, now next theorem, which connects all this stuff with integrable systems, is that this function f actually satisfies a system of functional relations, which can be, if you expand them in a series in both variables, z and psi, you get in front of each, and put to 0 coefficients in front of each term, you get an infinite number of differential equations for this function. And this infinite system of equations is nothing else than the two-dimensional Toda lattice hierarchy in the dispersionless limit. And this form of writing the equations of the hierarchy is known as Hirota form, because before the limit, when you have dispersion, non-zero dispersion, the Hirota equations are written for the tau function, and they are bilinear. In this limit, when we rewrite bilinear equations for tau in terms of f, they are no longer bilinear. They contain exponents and so on. So they are more complicated, but this is what they actually are. Yes?
The conformal map is related to the Baker function of this tau function?
Yes, sure. I didn't say a word about Baker function because in this dispersionless context it doesn't exist like tau function itself. But instead of it, we have some function which is sometimes called S, prepotential, introduced by Krichyver. In fact, this function is a generating function for first derivatives of the function f. I don't need it, so it can be introduced, but it's another story. Okay, now important comment about all this stuff, that our data was the function u or sigma, so some information about the background charge. These formulas and the formula for the Green's function doesn't contain any data of such kind explicitly. So this means that any non-degenerate solution to the Toda lattice hierarchy can be used to describe conformal maps. And the different background densities, the different distributions of the background charge, just parameterize different solutions to the Toda lattice hierarchy. Okay, now let me pass to physical applications, to Hele-Shaw viscous flows or Laplacian growth. So first let me start with the simplest example. This deformation, when the normal velocity is proportional to gradient or normal derivative of the Green's function, in this case it's the same because the Green's function is equal to 0, so the normal derivative is just the same as the gradient at the boundary. So when this base point goes to infinity, we have this law. Velocity, let us consider that t is a time, t naught is just physical time, and then we have a velocity of the boundary. So this support of eigenvalues evolves with time. We put more eigenvalues into it, and its density is constant, and the domain enlarged, and shape changed. It changed according to this law, which is nothing else than the so-called Darcy law in viscous hydrodynamics, which says that the velocity, local velocity in the viscous fluid is proportional to the gradient of pressure. So the standard setup is as follows. We have a thin gap between two glass plates, oil on one side and water on the other. So water has zero viscosity in this approximation, and oil has some finite viscosity. And in this case, the function phi is just pressure in the viscous fluid, and we have a pump which drives everything to the right, and the form of shape of this interface changed. This is Darcy law, and because of incompressibility, the pressure in the viscous fluid satisfies Laplace equation. At the interface, it's equal to its normal derivative is equal to the velocity because of the Darcy law, and we have some this function phi is singular at infinity, which means that we have this pump at infinity. Another, the same problem can be considered in different experimental situation when we have radial, I call this radial Hele-Shaw cell. This device is called Hele-Shaw cell. These two plates and the fluid in between. And so we have a water droplet. Some water comes from this tube, and oil just drops from the edges, and the shape evolves. And here, what is experimental? Some experimental pictures of what happens. So this, what is inside is water, and outside is oil. So this is the early stage of this process, and this is a somewhat very long time passes. After some long time, this picture evolves into this. So this is a picture of the real experiment after Harris-Winney. I forgot to say that everything is true only in the very important approximation that we have zero surface tension here. This means that the pressure is constant everywhere on the boundary, doesn't depend on the curvature. But in physical situation, of course, there is some surface tension. But for these pictures, these pictures obtained when the surface tension is very small. So we can hope that, in some sense, in some regimes, this approximation is good. Okay, now let me continue with integrable structure of the Laplacian growth problem. It was noticed by Richardson. Then under this process, the harmonic moments of the exterior are constant. And the area grows linearly with time. So this is exactly what was our setting before. I told it just another way around. I started from these harmonic moments, constructed explicit deformations such that all of them are constant except area. So this was exactly the simulation of the Hele-Shaw flow. Okay. Now the integrability was clarified in our old work with Mark Minet, Weinstein, and Paul Wigman. And we constructed this dispersionless tau function for this case, conformal map, Green's function, all this, the same formulas you see, but for particular background charge, which is constant in this case. Later, it was realized that, in fact, all this can be repeated for any density of the background charge, and in this way we can work with any solution of the total lattice hierarchy. Now, the more recent thing is how this structure manifests itself in the problem in the channel. In this case, there is a picture like this. Here is air instead of water. Air, in this context, is considered as a zero viscous liquid, and here is oil. And the result is that this problem is also integrable, can be embedded into the same total lattice hierarchy, and in some sense, this experimental setting is even better than the radial one, because in this case, some very intriguing connection with ramified coverings of Riemann surfaces emerged. So this picture is related to the algebraic geometry of Riemann surfaces. Okay, now let me pose the problem on this in more detail. So actually we work with not in channel but in a cylinder with periodic boundary condition in this transverse direction. So here is oil, here is water to the left. So we have two domains, D plus, it's oil domain, and D minus, water domain. And the problem is like this. This is a moving boundary problem, similar to the radial one, but with different conditions. So we still have a Laplace equation in the oil domain. We have periodicity in this transverse direction. So R is a radius of the cylinder. We have zero on the boundary. And this singularity at infinity, which says that we have a pump far away, which with constant rate. It works with constant rate. Now again, this problem can be reformulated in terms of a conformal map. Now it is a conformal map from the right part of the plane to the right of this curve to the right half plane. This is a physical plane, this is a mathematical plane. So the conformal map is W of Z. This is our cylinder. And everything can be done in terms of these conformal maps, but perhaps easier, and to connect this stuff with the previous one, is to introduce an auxiliary physical plane and an auxiliary mathematical plane. So consider such conformal map from this capital Z plane to the small z plane by this simple logarithmic map, and introduce the cutoff here, which will be useful because the potential here will be singular. And here we also have a simple logarithmic map. So this picture maps to our previous one. And all what we have to do is to re-express the normal velocity of the interface here in terms of normal velocity of this auxiliary interface. It appears that these two problems, this radial one is equivalent to the one on the cylinder, but here we have a constant density of background charge, and here it's not constant. It's just what was in the second example in the beginning. It is proportional to 1 over z squared. So on this auxiliary plane, it's singular. And in fact, these two problems are isomorphic. So the normal velocities are can be easily recalculated. and we get that the physical normal velocity of the interface on the cylinder is just the what we want. This is just the Darcy law on the cylinder. So the problem is equivalent, and we can construct the tau function for this problem on the cylinder. It can be represented either an integral over auxiliary physical plane or the physical plane itself or whatever. And there are two important properties of this dispersionless tau function, which are in some sense more interesting than and simpler than the ones. There are similar properties for the tau function for radial problem. Here we have this property, which is just homogeneity. It says that this is a homogeneous function of degree 2 in all variables and in the parameter r, which is radius of the cylinder. It's convenient to introduce the inverse radius, call it beta. And then the beta derivative of this function, this is the second property, is given by action of this differential. It's not actually not non-linear differential operator, because here we have linear terms, but here we have a product of two linear terms. So it's quadratic in derivatives. And the experts in Hurwitz numbers just recognize here the famous cut and join operator, which is used in that science. Okay, here is an example of a simple flow of the case when only T1 is not equal to 0 and all others are 0. In this case, the conformal map is explicitly given by this formula, only 3 terms, and the picture is like this. So the interface is trachoid in this case, and there is some critical time when this curvature becomes infinite. This is a finite time singularity, which are known to exist in Laplacian growth problems with zero surface tension. And in this singular time, this curve becomes just cycloid. So in this example, everything is very explicit. And now let me pass to the ramified covariance, to Hurwitz numbers, very briefly, because I guess time is not very not enough time. So we consider degree decovariance of Riemann sphere, CP1. Sigma can be some Riemann surface, in general of high genus, but at the end we will work with genus 0 surfaces. So covariance of CP1, maps of CP1 to CP1. So this map has some ramification points, which can, each ramification point can be characterized by a ramification pattern. This means that so this is the base curve, and this is sigma, and this is CP1. So above any point on the base curve, we have a finite number of curves because there are sheets, finite number of sheets. The covering is algebraic, so this is a finite number of them. And the case of general position is that the point is not no ramification. So we have different sheets which are separated. And this picture corresponds to partition like this. So each type of the ramification can be characterized by a partition or by Young diagram. So this one is the simplest. This is just column Young diagrams. We may have more complicated situation when there is the two sheets interchange when we come around this point on the base. So the example is the function square root of z. Then the standard example from theory of complex variables from textbooks, that two sheets just change when we go one time around this point, and if we go the second time, then we come to the initial sheet. So this is the simplest and general. So if the point is ramified, then this is a general position. So in this case, the corresponding diagram will be like this. So this corresponds to two boxes here, and others are we have so one another. So there are so many boxes as a number of sheets. So it's D. This number is called D on the slide. There may be more complicated patterns, like, I don't know, so many sheets can be interchanged, and in general this corresponds to Young diagram of arbitrary shape. And the mu's are length of rows of this diagram. This is the total degree equals to total number of boxes. And what we need is actually what is called double Hurwitz numbers. This means that there are two fixed points on the base curve which may have arbitrary may carry arbitrary ramification pattern corresponding to diagrams mu and mu bar, and necessarily there are some other ramification points, but our condition is that all of them are simple. So arbitrary can be only in 2 points. And these numbers are denoted like this. It contains information of all of the total degree of the covering, of the number of simple points, and of the patterns of ramification here and there. There is of course, the condition that the degree, all of them have the same degree, so the total number of boxes here is equal to that one here. Okay, now what people usually do after Andrei Kunkov, they construct the generating function of all these numbers. And the Hurwitz number, I forgot to say that the Hurwitz number is just counts the number of such coverings with this type of covering. This number is finite. It's not always integer, but this is a rather technical point. I'm not going to discuss it now, because if the surface has some symmetry, then to obtain a good theory, one has to divide by the number of elements of the symmetry group. So they are not always integer, but basically, in general, case they are integers. So one constructs a generating function of this form. So there are these Hurwitz coefficients. Q is the auxiliary parameter which counts the degree, the sum over d, and beta is the parameter which counts the number of simple points. This is will be the same beta as in previous formulas. So this looks like expansion, formal expansion in a Taylor series of a function in infinite number of variables. Now, Kunkov's result is that this function exponentiated and with some simple prefactor here solves the two-dimensional total lattice hierarchy. Now, what we are going to do is to make the quasi-classical or dispersionless limit. So rescale times in this way, introduce the new parameter h bar, rescale like this, and introduce a new function with rescale, function of rescaled variables. So then it can be expanded into a series in H bar. Series is of this form, and now the Riemann-Hurwitz formula says that this genus G is not that it's expressed through the ramification data. So this is in fact a genus expansion. The functions which appear as coefficients are generating function for Hurwitz numbers corresponding to fixed genus of this curve, which is above. Okay. Now we consider the genus 0 when the curve above is just Riemann sphere. Then we have this series. It simplifies somewhat, and there is a relation to dispersionless tau function for the Laplacian growth problem on the cylinder. That this function is up to some simple terms here and some redefinition here is exactly the dispersionless tau function for the Hele-Shaw problem on the cylinder. So this these two problems, algebraic geometrical problem of coverings of Riemann surfaces and this Hele-Shaw problem or Dirichlet boundary value problem, which is behind it, they are governed by the same master function. It is this function. I see. Okay. Last slide. So this is just conclusion and some references. So thank you.